So, let's see, how do I say, there are some problems that you're going to see on your test. You're going to see a problem either like this or on your test. And one of the things right off the bat, it kind of reminds me of intermolecular forces problems, where you have to kind of think big picture. Yeah. So what I would do, we have a bunch of solutions here. They're all the same molarity, 0.1 molar, and we have to arrange them. And don't let this kind of come back to haunt you, but so we have to arrange them in order of increasing pH. So we have the most acidic, right? Because that's the lowest pH, to the most basic. Now, what I would do if faced with this problem, I'm going to kind of walk you through it, is I would take each of those 7 and identify what they are. So terms we've used, let's see, what does SA stand for?
Strong acid.
Strong acid. How about SB?
Strong base.
Strong base, yep. WA, weak acid, and WB, weak base. Cool. We kind of got an idea about that. Now, in this part, we've talked about conjugates, okay? So next to my WA, I'm going to put, let's see, I'll put conjugate base, conj for conjugate base of weak acid. So that's kind of the yin and yang, okay? And next to the weak base, I'm going to put conjugate acid of weak base. So this is to say that these 2 differ by a proton and these 2 differ by a proton. Okay. So, NH3. Now actually, if you look, we've also got NH4 plus. Do those differ by a proton, right? Right off the, let's see, well, the fact, I'll put it in the form of not a question, but the fact that there's no Ka given for ammonium, NH4 plus, actually means that it must be weaker. This is a weaker acid than this is a weak base. Does that make sense to you? Because these are conjugate acid-base pairs. And I guess in context of what I just said, I would call this a weak base, that being the NH3, and I would call this the conjugate acid of a weak base. Does that make sense?
So is it also a weak acid?
Yes, it's a weak acid, but it's a weaker weak acid than the base is a weak base. Put another way, well, let's see, how do I say this? We said that if you have a conjugate acid-base pair like that, you could take the Kb times the Ka, and that's equal to Kw. Remember that? Okay. So actually, we could knock out the Ka for NH4 plus by just doing some
That's
math.
what I was thinking.
Yep. And what you're going to do is you're going to find it's times 10 raised to the negative 9th magnitude. So yeah, it is definitely weak acid. NH4 plus is a weak acid, but it's a wimpy weak acid. Okay, what about, let's see, I'm going to pick on formic acid and sodium formate. So what is formic acid? What is this guy? Well, is it an acid or a base? It's an acid. It is a strong acid or a weak acid? Well, the hint is it gives you Ka.
Maybe stronger?
Nope, it's a weak acid. And the Kas for strong acids say very large. Okay, like HCl, the Ka says very large. Yeah, and yeah, so that's a weak acid. Very good.
So very large, would that be like nothing lower than like maybe like 10 to the negative second or?
Well, it really says the words, 2 words, very large. Yeah.
Okay.
So it's very product favored, which means it entirely ionizes. That's your one-way arrow thing. Yeah. Okay, so how about sodium formate? Now, I didn't mention it with ammonium nitrate, but this guy right here, the nitrate, excuse me, not the nitrate, the sodium part, it's not going to add anything to your pH. But can you see where acetate, or excuse me, formate, sorry. Formate is like the conjugate base of the weak acid formic acid. So this and this differ by a proton. Okay. The other spectator, along with ammonium, this guy's a spectator, nitrate and sodium. Right. Well, I skipped nitric acid. What's nitric acid? Is it acid or base?
Oh, it's an acid.
Is it acid? Is it strong acid?
I'm not always sure how to tell the difference. Is this one strong?
This one's strong. There were
Okay.
7, and before you come to take your test in a week from Thursday, you probably need to double check, make sure that you know what the 7 strong ones are. But it's strong. There is no Ka value given. So
So is that really like kind of a hint for
kind of a hint, yeah.
if
Yep.
there's no.
Yep. This is strong acid. So we're probably liking to start our list with this guy. So sodium nitrate. Well, earlier I told you that the sodium is a spectator and the nitrate is also a spectator. So actually sodium nitrate, you dissolve it and it doesn't do anything with, because those are not, it's not a weak acid, it's not a weak base, it's not the conjugate, neither the cation or the anion are conjugates of weak bases or acids. Okay, so what about the last one?
Is it a strong base?
It is a strong base. Yep. So this is where you start to kind of sort them, and you know that this one's going to be last. So put a number 7 here. You have 7? Yeah. This one's going to be first, the strong acid. Put a number 1 there. And the reason I did this was I was trying to show you that after a strong acid comes the weak acid. Okay? After the weak acid comes the conjugate acid of the weak base. Okay, so I think these are easier than intermolecular forces. So we're going to do that for 2, this for 3. After the conjugate acid of a weak base, then we're going to go neutral, which is that sodium nitrate. And then then we're going to start basic. So the slight basic would be the conjugate base of the weak acid. So I'll put 5 there. And then we get to our weak base, ammonia, 6 up there. So I don't know. If I was going to do this, I would sort of dissect what each one is first. And then kind of go from there. So in other words, the order went like this. It went strong acid, and then weak acid, and then conjugate acid of weak base, and then neutral, and then conjugate base of weak acid, and then weak base, and then strong base. So if you can kind of correctly identify, and that's all assuming there's the same molarity. If they're different molarities, all bets are off. So here I have them, just like I said, strong acid, strong base at the bottom. Now the weak acid is a little bit stronger than the conjugate acid of the weak base. Neutral, weak bases, So the weak base is a stronger base than as the conjugate base of the weak acid. That's it. Okay. Whoops. So I think we're going to be okay for lecture, but we need to get to acid-base reactions before, and titrations before Thursday's lab. So acid-base reactions, you guys have done them before, and actually we've kind of looked at them in the context of Chem 2 recently. But on either side of the reaction arrow, you should be able to pick out your conjugate acid-base pairs, and you guys had some work at that before. So the acid is the proton donor, and the base is the proton acceptor on either side. So they differ by a proton. So you can kind of see how these differ by a proton here. Differ by a proton. One of the things, this is a good example of, you need to, like if you see this CH3COONA, think ionic compound, a salt, and it says AQ means you're dissolving it in water, and think of how it dissolves. Okay, so your Na plus leaves, what does that leave? Your CH3CO -1. That's a great proton acceptor. See how its conjugate is the weak acid, acetic acid, acetate ion. Differs by proton. Conjugate acid-base pairs. Okay, so I think I did look at this one. 16.5. Looks like this. All right. So this is kind of a weird question, I think. It says which of these bases will react with acetic acid, and it will proceed as much as possible to the right. So up in blue it says look for the formation of the weakest acid or base. So it always goes, and I think the examples I showed you at the end there, I didn't emphasize it, but it always goes from strong to weak. So here we have, this would be the first example. If you react acetic acid with water, that's A. Does it seem likely that on the product side that you're going to get the acetate ion and the hydronium ion? Well, it seems like it, but this guy over here, this is a very strong acid. So you're kind of going uphill here. Your things are to pick which of the following will proceed furthest. So which of these A through D seem like they will happen? And to me, I have a red flag here because it, again, looks like you're going uphill. H3O plus is very strong. So I think A is not likely. So then you pick NH3. What if instead of water you had acetic acid reacting with NH3, and what would it form? And I think that's going to be favorable. Okay, because if you look over here, these are weaker. So it's always going to go from strong to weak. So it's a little squishy. But see what you think. And actually, it's an odd one, so you should have the answers in the back. Oh, come back. And then the next one looks like this. There you are. Reactions will always favor from strong to weak. All right, so predict the direction to be favored.
Is that the same thing? Whichever side has the stronger.
Yeah, and if
acid
it's stronger over here, then it's actually going to go from right back to left again. similar to 7. Okay? All right, on to buffered solutions. I like this topic. It's kind of fun, I think. When we had lab, and actually we'll have buffered solutions out again for this Thursday, because to calibrate the pH meters and stuff. But a buffered solution is great for resisting pH change. So in other words, if somebody has a vat of something and they say, well, that's a buffered solution, that means you can dump in a little bit of H plus and it won't become acidic. You can dump in a little bit of OH minus and it will not become acidic. It fights pH change. You're like, how does that work? Well, this is how it works. So the secret to buffered solutions is this. It needs to have the hydroxide ion there in case somebody sprinkles it with the hydrogen ion. So it can neutralize the hydrogen ion. And then it needs to have a certain amount of the hydrogen ion in there in case somebody adds a base to it, so it can fight pH change. So basically, it needs to have a base and an acid, and the third requirement is that those bases, that base and the acid, need to be able to coexist. You're like, really? Well, I thought if you had a base and an acid, they would react and form water. It needs to have an acid to react with the hydroxide ion, needs to have the base to react with the hydrogen ion, and the acid and base cannot react with each other. They need to be friends. And a great set of friends are a pair, a conjugate acid-base pair. There's, that's the most common buffered solution. So in other words, what you see people do is if they're like, oh, I need a buffered solution, then they go ahead and they dose it with the conjugate acid-base pair. So I asked Carl, I'm like, do we give them this equation? He said yes. So this will actually be on your, I'll provide this for this test. But you need to know how to use it. So don't say, oh, well, it's there, I just plug and chug. Well, not exactly. So I call this the HH, or the Henderson-Hasselbalch equation. I'm going to write it here so we can kind of take a look at it. This only applies to buffered solutions. Don't try to use the Henderson-Hasselbalch equation for something that is not a buffered solution. It says that the pH of your buffered solution will be equal to the pKa, so that means, well, that's what it means. Basically, we talked about Kas, and in order to get the pKa, you take the negative log of the Ka. Plus the log, that has to be base 10, of the molar concentration of the, I usually just say base, molar concentration of the base to the molar concentration of the acid. And when I say base and acid, those are conjugate acid-base pairs. Right? And we'll see what that looks like. So I don't always do this, but I went ahead and showed you the proof that this equation, the Henderson-Hasselbalch equation, actually is like you can see a weak base. A weak acid ionizing to form H plus and B minus. There's the Ka expression for that weak acid. You apply the log function to both sides, blah, 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 and you actually come up with the Henderson-Hasselbalch equation. pH is equal to pKa times the log of the ratio of molar concentration of B minus to HB. So anyway. Okay, there's your Henderson-Hasselbalch equation. There's one more form that sometimes is preferred to this, and it has to do with kind of getting away from the molar concentration of the ratio of the base to the acid. So assuming that your conjugate acid-base pair are swimming around in the same volume, right? The molar concentration of the base is the moles of base divided by that common volume. Acid, moles of acid divided by that common volume. If we plug those up there, actually our volumes will cancel. And now we have an alternate, form of the Henderson-Hasselbalch equation. So in other words, instead of this ratio, molar concentration, if it's easier, we can go moles of base. Oops, VASS. Moles of base to moles of acid. Whatever's easier. Okay. So we have two forms of the Henderson-Hasselbalch equation. Again, has to be a buffered solution. This can be very helpful. And I, on Twitter, pushed out there biological importance of buffered solutions, because I think that's kind of interesting. They fight pH change. So, a couple of assumptions in order for your buffered solution to be working. First off, the amount of ionization of that weak acid is negligible. The amount of hydrolysis that your weak base has interacting with water is also negligible. None of these very large, okay? So that means your Ka and Kb have to be moderate. And actually, if you're making a buffered solution with a conjugate acid-base pair, this will be the case because the presence of one will kind of diminish the ionization or hydrolysis of the other. So it's a fair assumption that will be the case. Right. So pH is equal to pKa plus log of this ratio. So pKa is a constant. Okay, so this ratio here is kind of a driving force to what your pH will be. Now there's a difference of what your pH will be and what we call buffer capacity. You can imagine that you prepare your buffered solution, you're like, hey, that's wonderful, but if you like really douse it with acid or base, it may not be able to accept all of that acid or base. It doesn't have the capacity. The capacity then has to do with the ratio and also the molar concentrations themselves. So when we talk about buffer capacity, it's like I said a minute ago, we are saying how much can it accept with regard to acids and bases and still resist pH change. So it is a better buffer solution the more this ratio approaches 1. So I'm going to go ahead and I'm going to approach the number 1. So what is base 10? What is the log of 1? 0. As that approaches 1, then this approaches 0. This term does. And the cool thing about that then is that means that your pH of your buffer solution will be your pKa, which you get from a table. So the larger the concentrations, then the greater the buffer capacity. So those two things kind of work together to make it the best buffer solution it can be. The ratio of the conjugate acid-base pair is nearly 1, and we have reasonably high molar concentrations of both. So this says that, what does it say? 10 to 1, yeah. So if this ratio becomes 0.1 or 10, okay, if it's outside of that, then you're going to have issues with your buffering capacity. Okay, so those are the two forms of the HH, or the Henderson-Hasselbalch equation. Now I think we get to do an example. Oh, almost. Well, I told you we're shooting for 1 as the ratio of your conjugate acid-base pair, which makes that term 0. So you can kind of see in that case, your target pH, you can kind of pick up from your pKa. Okay. All right. So you can do this the easy way or the hard way. We're going to start with the easy way. The easy way is you simply take your container, you want your buffer solution in, go ahead and add some water to it and add a little bit of the conjugate acid and the conjugate base. The other way, and we'll be talking about this on Wednesday, is to go ahead and force the production of your conjugate by either adding a strong acid or a strong base. I'll show you what that looks like. Something on the front end to force it to react, to convert some of your weak acid or weak base into its conjugates. So let's look at the easy one first. So I'm hoping when you look at this, you can kind of see this is a weak acid, the CH3COOH, it's acetic acid, and I'm hoping that you see in that salt, the CH3COONA, that actually is the conjugate base of that weak acid. They differ by a proton. So how many grams of sodium acetate do we need to add to 100 milliliters? Let's see, how do I do this? I hadn't thought through this. Okay. Doop, 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 doop. So this is 100 milliliters of 0.125 acetic acid. And we are going to add question mark grams of CH3COONA. And it says, I call it the target pH is 5.00. So now if I go ahead and bring the Henderson-Hasselbalch equation over here, our target pH, well, I'll just go ahead and rewrite it. pH is equal to pKa plus log of the ratio, and we're going to go moles instead of molar concentration, I think. Moles of base to moles of acid. Our target pH, 5.00. pKa, we're going to get that from the table. By the way, our acid is CH3COOH, so we're going to get that from the table. So here we have the number of moles of acid, CH3COOH, and the number of moles of base. That's your CH3COO minus. So this comes from your sodium acetate. That's it. That's how that looks. What do you think? Not bad. So can we use, oops, goodness. Can we use molarity and volume to get moles of CH3COOH? Yep. So we have those hidden. Must be a throwback. Oops. So a common mistake I see on tests, I don't know necessarily about homework, tests, we all just tend to kind of freak out. But even if you're like, it's a buffered solution, I'm probably going to use the Henderson-Hasselbalch equation, you kind of lose track of what is your acid and what is your base. When I'm working these on the answer key, I usually say, what is my acid acid and what is my base. From the table, we got the Ka for the weak acids, 1.8 times 10 to the minus fifth. We can get pKa from that, right? Let's just apply the log function, or apply the p function. We don't need it here, but, so I don't know why I went ahead and knocked it out. But be able to go back and forth between, for a conjugate acid-base pairs, the Ka and the Kb. Ka times Kb is equal to Kw, so Kb is Kw divided by Ka. So if we needed it, we can knock out the Kb for the acetate ion is 5.6 times 10 to the minus 10th. I think the reason I'm bringing this in is oftentimes, well, it's possible to have a buffered solution where you know the Kb for your weak base, but you don't know the Ka, so you can't get the pKa. So you kind of go backwards. I know. You have to be able to do that. Okay, so let's knock out what our pKa term's going to be, and it looks like this. So if we apply the p function to the Ka, we take a negative log of 1.8 times 10 to the minus fifth, and we get 2 sig figs, 4.74. And what the rule of thumb is your pKa should be kind of close to your target pH. So I'd say that's 4.74 is pretty close to 5. So there's our Henderson-Hasselbalch equation. Now there's a few ways. We basically have to tease out the N of the base. Okay, there's a couple ways to work this. Kind of logistics. This way I'm going to kind of rearrange the Henderson-Hasselbalch equation to isolate the moles of the base. And so remember, if I want to get to a quantity that I'm taking the log of, if I take both sides, 10 raised to that power, 10 raised to the log of this quantity is that quantity. So it looks like this. Basically, I take 10 raised to these powers. So now we have, I think I'm going to switch to moles here in a minute, but now we have the ratio of the molar concentration of the base, molar concentration of acid is equal to 10, raised to the negative pH, raised to the pH minus pKa. Yep, then I switched to moles there. Instead of molar concentration, moles. So moles of base by moles of acid is equal to 10 raised to the quantity pH minus pKa. Going all the way to what the moles of base would be, we multiply both sides times the moles of acid, and it looks like this. So now you have something where we know all of those values. Well, almost. The moles of acid we're going to have to get from molarity and volume of acetic acid. We can do that. That's a Chem 1 problem. So this is getting to the moles of CH3COOH. If we take the volume, 100 milliliters, I would have put this last term second to convert to liters, and then use molarity to get to moles. Rounding it to, it looks like I've lost my decimal up there, rounding it to 3 sig figs. This is the moles of acetic acid that we've got, 0.0125. Yeah, there are quite a few little things to take care of, aren't there, in this problem? So now we're ready to plug and chug. So the moles of base is equal to the moles of acid, 0.0125 moles, times 10 raised to the quantity, our target pH, minus the pKa. So 5.00 minus 4.74. I think we're only allowed 2 sig figs, is what I get. But, that's what my answer says. Well, I allowed myself 3. I still think their case could be made for only 2 sig figs then. But anyway, the moles of base is 0.0227 moles of, remember what your base is, that's your acetate ion, CH3COO negative 1. And we're still not done. We're close. Our question was, what is the mass of the sodium acetate we need to use in order to get this moles of acetate ion? So we're going to need the molar mass of sodium acetate, which I didn't do here. So it's a separate molar mass you're going to see coming up. So if this is our moles, target moles of acetate ion, we can use the stoichiometry that we have 1 mole of sodium acetate, 1 mole of acetate for every 1 mole of sodium acetate. That third term is the molar mass that you're still here in Chem 2 need to show me calculating the molar mass of sodium acetate. 82.03 grams per mole. In my intro class, we're talking about this sort of calculation from moles to grams. So moles will cancel. We're left with grams of sodium acetate, which is what we need to be left with. Round to 3 sig figs. Looks like you need to measure out 1.87 grams of sodium acetate and add it to your 100 mils of 0.125 molar acetic acid in order to buffer it to pH 5.00. So what I did was to pull, just since it's kind of fresh on your memory, right, or we just did it in class, I pulled 17.7 up. So this will also be due, let's see if I got it out here, on Wednesday. $17.7, wow. Okay, well I've got 17.789. I'll push these out here. But hope this is right. It looks like what we've been doing. Dealing with formic acid and formate here, similar to acetic acid and acetate. What concentration should be present? So in this case, it's not as complicated as what we just did. You just have to come up with the molar concentration of the formate ion. And it gives the molar concentration of the formic acid.
Is 8 and 9 going to be assigned on Wednesday? Because it is in there at the back. I was just curious to see if we can,
I think so, yeah. Yeah, because I can't remember any reason they wouldn't be. Oh, but I'm looking at this now, and this is 8, and this actually does the other thing, and we're going to talk about this Wednesday. You can take a look at it, but we haven't talked about how to work 8 yet. Well, we did talk about how to work 7. So, good question. Okay, so we'll just stop there.